phone recorder. Okay, so for today's the lecture, okay, so we first finish the last question of the discussion worksheet, okay. All right. Yeah, if you have any question, okay, still type in the chart window, okay. All right. So for here, okay, so for this reaction, okay, it looks like E2 elimination should work, okay. So because you have some kind of leaving group, okay, and then there's kind of beta hydrogen, okay, so you get more substitute alkene, okay. All right. So yeah, if you directly do the E2 elimination, okay, so looks like you can get this one, okay, but the reality you get wrong stereochemistry, okay. So yeah, we can try it, okay. So yeah. For this one, okay, so you have to make sure the beta hydrogen leaving group has anti-coplanar, okay. Now, so far, all point towards you, okay. So in this case, you have to need to be the rotate the bond, okay. Rotate one kind of carbon, this carbon, and this carbon, okay. So we move hydrogen here, and then this ethyl here, and this the methyl here, okay. Right, we get like this. Methyl become kind of the wedge bond, okay, and then the ethyl become kind of the dash bond, okay. Right, same thing, okay. So we rotate the second carbon, okay. Somehow like 120 degrees, okay. So I want to move this chloride here, and then this ethyl here, and then this hydrogen here, okay. And after rotations, okay, so that you can put it like this, okay. Hydrogen, and then ethyl, okay. So that's make the beta hydrogen and those the lean group, okay, anti-coplanar, okay. So and then we can do the elimination reaction, okay. So once you done the elimination reaction, okay, so this part gone, okay. Right. So what you left is kind of the two ethyl, okay. You can see kind of both the dash bond, okay. So that means two ethyl group, okay, on the same side of that bond, okay, and then methyl hydrogen on another side, okay. Right. So that means you cannot get desired product. This one should kind of trans, okay. So here you get cis, okay. Right. So in this case, yeah, if you really want to get here the desired chemistry, okay, so the stereochemistry, okay, so you need change the stereochemistry of this one, okay, this carbon, okay. So that's pretty easy, okay. So we learn that, okay, so we can do the halogen change, okay, highlight change, okay. So yeah, sodium iodide, okay, in the acetone. Right. So that's you will do SN2 reactions, okay, in what stereochemistry of this chloride, okay. Right, so it's still draw like this. Nothing carbon, nothing change on the left carbon, but here the right carbon, okay. Iodide become kind of the dash bond, and then yeah, hydrogen kind of the wedge bond, okay. Right, so in this case here when you do the elimination, okay. Right. In this case here, when you do the elimination, okay, so you should get kind of right here the stereochemistry, okay. So yeah, that matter, okay. So you can use kind of sodium ethoxide, sodium methoxide, okay. So yeah, that's your get kind of here, okay. All right. So make sure that you understand what's going on, okay. So normally speaking, kind of in synthesis design question, okay. So you cannot finish the conversion in one step, okay. So yeah, life is not so easy, okay. So at least 2 steps, okay. So all right, okay. So that's finish this one, okay. And before the lecture, okay, so a couple of things, okay. So first kind of exam, okay. So we have exam, 1, okay. So tonight, okay. So I open it at kind of 6 o'clock until 8 o'clock until 12 o'clock, okay. Real question like I cannot tell you anything about the question on the exam, okay, but it's just kind of fully prepared, okay. Yeah. All right. And so I have actual kind of office hour, okay. So yeah, from 4 to 5, okay. So just after this lecture, okay. After this lecture, I will keep my Zoom open, okay. So if you have a question, okay, any question, okay. So yeah, the homework or kind of some kind of the practice, okay. So you can come ask me, okay. And from 4 to 5, okay. And also keep in mind, okay, so yeah, the actual credit homework is also due today, okay. So yeah, there's kind of the online open kind of Dropbox, okay. Yes. All right. So there are totally 25 questions, okay, in the exam, okay. All kinds of questions, okay. So yeah, multiple choice questions, sorting questions, ranking question, and then yeah, mechanism drawing question, complete reaction questions, okay, and maybe some other kind of product drawing questions, okay. So step 2, yeah, you use any strong base, strong nucleophile, that will be fine, okay. Sodium hydroxide is good, okay. Yeah, so sodium hydroxide is good, okay. Yeah. All right, any question about the exam or kind of the worksheet? All right, if there's no further question, okay, so we continue chapter 11, okay. So chapter 11, last time we talked about kind of mechanism 2, okay, so addition of your halogens, okay, you add a pair of the chlorine or a pair of your bromine onto kind of CC bond, okay. And the stereochemistry exam will be appear on smart group. Yeah. So we'll do the exam, okay, on smart work, okay. So I will turn the exam on 6 o'clock, okay. And close it at kind of 11:59, okay. Yeah. All right, okay. So the stereochemistry, okay. So we will follow kind of the anti-addition, okay. Regiochemistry, okay. So yeah, that's theoretically speaking, kind of regiochemistry, okay. So should be similar like mechanism 1, okay. So yeah, should be kind of a nucleophile add to kind of more substitute carbon, and then electron add to kind of last substitute carbon, okay. But for this reaction, because they're both nucleophile and electrophiles kind of both are kind of bromide, okay, that's hard to distinguish. Okay. So in this case here, there's kind of no regiochemistry for these reactions, okay. So but later we will learn another reaction, we'll have this reaction, have kind of regioselectivities, okay. All right. Okay, so for the addition of the bromine or chlorine case to CC bond case, so the alkene case. So depends on how many the substitute group case, how many alkyl group on the alkene, they will have kind of different reaction rate case. And basically speaking, more alkyl group case or more substitute kind of the alkene, you have kind of a higher reaction rate case. And so here's showed you some kind of comparison case. So yeah, first one has no any kind of the alkyl group case, reaction rate is 1 case. If we increase kind of mono substitute case, only one alkyl group, that's kind of 100 times kind of increased reaction rate case. And disubstitute case, so yeah, for the increase 2000 times case, and then followed by kind of the trisubstitute, and then tetrasubstitute case. So tetrasubstitute kind of 10 to 2 times 10 to 6 case, extremely kind of faster case. Why is that case? So reason for that kind of remember for the alkene addition case, so we call kind of the electrophilic addition, okay. Right. So if you have some kind of alkyl group, okay, right, and then alkyl group actually has a little bit of weak electron donating ability, okay, to the CC bond, okay. Right. So yeah, if you have only one alkyl group, okay, so that's can donate some electrons into CC bond and then make it kind of more electron rich, okay. More electron rich, you like to pick up kind of nucleophile, do the addition reactions, okay. So if you have 2 alkyl group, okay, and then even more kind of the electron rich, and then 3, and then up to 4, okay. So the more alkyl group, you get kind of the rich in the electron of theta bond, and then easier carry kind of electrophilic addition reactions, okay. So that's the just pretty easy to understand, okay. All right, and then in addition to kind of the alkene, okay, so you can also do a similar reaction to the alkyne, okay, CC3 bond, okay. All right, questions?
Do we need to know that table on the last slide?
No. So you just remember it, okay? So you don't need to remember any number, okay? But you need to remember, okay, so reaction rate, okay? So how fast kind of which is kind of faster, okay? So more alkyl and the higher reaction rate, okay? So don't need to remember the number, but you need to remember the order, okay? Remember the order, okay? Resonance stabilization makes the rate most slower, okay. Here, okay, so yeah, there's no resonance, okay, so yeah, if there's a resonance, okay, so yeah, in the end of this chapter, okay, we'll learn one kind called conjugated addition, okay, so there's we involve some resonance, okay. So far, no resonance, okay, so yeah, no resonance, okay. All right, okay, so addition of the bromine to alkyne, okay. So this reaction actually kind of also kind of the anti-addition, okay. And so if you control the amount of the bromine, okay, so you can add just the one pair of Br onto the CC3 bond, okay, and then just kind of we call it the dibromo kind of alkene, okay. All right, example shown here, okay. All right, and I also draw you guys probably one example, okay. All right, so we have this alkyne, okay, and then if we add just one equivalent kind of the Br2, okay. All right, so yeah, for this reaction, okay, so yeah, still follow kind of the anti-addition, okay, so keep in mind anti-addition, okay. All right, and in this case, okay, so yeah, each carbon pick up one bromide, okay. All right, but anti-addition, okay, so one bromide going up, one bromide going down, okay, so that's your anti-addition, okay. An example also showed here, okay, so we have anti kind of major product, okay. And but yeah, if you use kind of the excess of so if you use excess of the bromine, okay, so you generate kind of we call it tetrabromide, okay, so we add kind of two pairs of Br, okay, onto the CC3 bond, okay. So yeah, in this case, yeah, for example, yeah, I use kind of the excess of the Br2, okay, so that's your totally you can get kind of the 4 Br, okay, onto the CC3 bond, okay. Yeah, all right. Okay. All right, and then we move to the next little bit harder reaction, okay, halohydrogen reaction, okay. So far, yeah. So mechanism 2, okay, we already learned the addition of halogen, okay, so meaning kind of Br2 and also Cl2, okay. So when you do this reaction, okay, so yeah, normally speaking, you use some kind of inert kind of solvent, okay. So yeah, that solvent kind of no reaction, okay. For example, methane chloride, okay, or chloroform, okay, or some kind of tetramethyl, this kind of this called kind of carbon, the tetrachloride, okay. But yeah, if you use some kind of the water as solvent, okay. Okay, and then the water will be work as kind of nucleophile, okay, and then you generate kind of the different product, okay, called halohydrogen, okay. So that's the second reaction under the mechanism 2, okay, so called kind of the halohydrogen, okay. Reaction, halohydrogen reaction, okay. All right. All right, so the general reaction actually already showed there, okay, maybe draw it again, okay. So you have CC double bond, okay, and then you have kind of the halogen, okay, so Br2 or Cl2, and then in the water, okay, at the nucleophile, okay. Because the first step, okay, for the halohydrogen reaction, same as kind of addition of the bromide or kind of chloride at inner atmosphere, inner solvent, okay, you generate kind of the triangle intermediate, okay. But because the water is kind of in excess, okay, the solvent, okay, and then instead of Br minus or Cl minus open this triangle, okay, so the water will come in, open the triangle, okay, and give you kind of we call halohydrogen, okay. And HX, okay, so doesn't matter, okay, so yeah, if you don't want to draw it, that's fine, okay. All right, so for halohydrogen reactions, okay, so yeah, same as kind of all other kind of mechanism 2 reactions, okay, anti-addition, okay, so yeah, that's kind of X add from top, okay, and then OH add from bottom, okay. So just show you one example, okay. So that's the stereochemistry, okay. All right, so this time I use chlorine as example, okay. So for this one, okay, because the kind of unsymmetrical, symmetrical kind of arcane, okay, so it doesn't matter, okay, so where the chloride or kind of OH adding should be large bond, okay. And also you can generate kind of it's the enantiomer, okay. Yeah, so a pair of the compound, okay, anti-addition, okay. And the more difficult case, so that's you understand, more difficult kind of radiochemistry, okay. Right. So radiochemistry, you just keep in mind, okay, so OH add to kind of more substitute the carbon, okay. And the reason for that is kind of some question. Yeah, pretty much, that's you can do 1-to-1 ratio of your bromine to kind of arcane, you can do the 1-to-1 ratio, normally this reaction, actually this week, okay, so remember this week lab, okay, we did some kind of the alpha styrene addition to kind of the NBS, okay, so I yield many times, okay, so you have to make sure 1-to-1 ratio of the alpha styrene and those NBS, okay, so that's do it here, okay, so water from aqueous kind of the acetone, okay, for this week's lab, okay. All right, okay, so why is that, okay, so hydrogen on the more substitute carbon, okay, so reason for that kind of we generate kind of the intermediate, okay, so okay, so first draw you guys the reaction, okay, radio selectivity, okay. All right, so now we have a kind of unsymmetrical arcane, okay. So if you have unsymmetrical arcane, okay, so you have to figure out here which one pick up the hydrogen, which one pick up the OH group, okay. So this species here are actually called kind of halohydrin, okay. This kind of compound, okay, halohydrin, okay. Right. So for this reaction, okay, so water goes kind of more substitute kind of the carbon, and then bromine goes to another carbon, okay. So the why is that, okay, so we are reason for that kind of the intermediate, okay. For this reaction, okay, so once you add the bromine, okay, so I will ignore the kind of first step, okay, so the first step same as kind of the other the bromination, okay. Right, you generate this kind of the intermediate, okay. Generate this kind of intermediate, okay, so this positive charge won't stay at kind of this bromine, okay, bromine, okay. You still kind of delocalize, okay. Right, and then you find kind of the this positive charge kind of the likes to go to kind of the more substitute carbon, okay. The reason for that kind of way is kind of carbon cation stability, okay. So the tertiary more stable than secondary, and then more stable kind of than the primary, okay. So if it goes to here, that's pretty much like a tertiary, okay. So if it goes here, pretty much like the primary, okay. So that means kind of this carbon like pick up kind of the positive charge, okay. All right, in this case, okay, so when the water come in, okay, so water is nucleophile, electron rich, okay, want to attack this carbon, open the ring, okay, and then you get kind of the final product like this. Okay, so that's the thing keep in mind, okay, and also one way, okay, so when I was kind of undergraduate, kind of I learned this reaction, okay, I was thinking of how do you remember the words bromine goes, the words kind of the OH goes, okay, so you just think about kind of bromine as the water, okay, as the hydrogen, okay. So that you can apply kind of the Markov-Nikolov rule, okay, Markov-Nikolov, okay, rich get richer, okay, carbon with more hydrogen on, okay, you get a hydrogen, and another species goes kind of carbon with the more alkyl group on, okay. All right, so in this case, if you think kind of the bromine is kind of hydrogen, then kind of bromine goes kind of carbon with more hydrogen on, okay, and then another species OH goes kind of more substitute carbon, okay. So that's the keep in mind, okay. All right, okay, so that's the one example, okay. Another example, okay, so that's come to kind of this week lab, okay. So this week here we did some kind of the halohydrin reaction, okay. Remember, okay, so we have kind of the alpha methylstyrene. Okay, this guy. Okay, right. And then yeah, you did some kind of the NBS is kind of same as kind of bromine. Okay, and then we use aqueous kind of the acetone. Okay, aqueous acetone, and the has water provide that kind of the nucleophile. Okay. Right. Okay, so remember, okay, so if you did the pre-lab, you understand, okay, ask you kind of you have two possible products, okay, one's like this, okay. OH. So one's kind of like this, okay, another one like this, okay. So yeah, because this is unsymmetrical alkene, okay. All right, so you have to determine which carbon, okay, so these two carbon, which carbon pick up the bromine, which carbon pick up kind of OH group, okay. So we can figure out kind of by the NMR next week, okay. But here after you learn this reaction, kind of easy figure out, okay. So yeah. Okay, so yeah, ask you guys, okay. So which is the major, top one or bottom one? Okay, type in chart window. Yeah, that's right. Okay, bottom one. Okay, that's right. Okay. So that's even without next week kind of the NMR, you can already figure out based on kind of knowledge we learn in this chapter. Okay, always goes kind of carbon with more separating group on it, and then bromine you treat that kind of hydrogen, goes kind of the carbon with more hydrogen attached. Okay, good. All right, and then there's do one more example. Okay, so that's the combine both the stereochemistry and those the regiochemistry. Okay. Okay, we have this species. Okay, so we try to do the kind of the hydrogen reactions. Okay, so yeah, Br2 and then water. Okay, all right. So yeah, first, okay, so for this reaction, okay, so I will do kind of kind of intermediate. Okay, so yeah. Hydrogen, okay. Hydrogen, and then there's the acyl group. Okay. All right. Okay. And then the nucleophile will come in. Okay. So yeah, when the nucleophile come in, okay, so yeah, we'll attack kind of this carbon. Okay. So that's the water. Okay. So attack the more substitute carbon or open the ring like this. Okay. All right. And then yeah, you generate kind of the one product, okay, like this. So I ignore kind of the some base pick up the OH, okay, the hydrogen, okay. So yeah. All right, and then that's the one possible product. Okay. Another one's kind of the you have kind of triangle going down, okay, okay. So we draw it here, okay. Hydrogen, and then hydrogen, ET, okay.
Right. Why did the left carbon pick up an ethyl? In the first solution, you show the left carbon picking up an ethyl.
Oh yeah, not ethyl. Okay, so that should be hydrogen. Sorry.
Okay.
Yeah, that should be hydrogen. Yeah, the carbon with more hydrogen pick up the bromine. Okay. Yeah, the ethyl group. Yeah, we only have the one ethyl group. Okay. Yeah. All right. Okay, so yeah, we have another intermediate. Okay, so in this case, the water also attack on the most substitute carbon, and then you open the ring like this. Okay, so in this case, we generate another product. Okay, yeah, the hydrogen, and then also hydrogen here. Right, Br, and then OH, and then acyl. Okay. Right. So yeah, the relationship between these two, okay, should be enantiomer, okay. Yeah, actually you combine R and S, okay, so there's only one steric center, okay, so yeah, for this pair of molecule, okay, so this one and this one, okay. So actually kind of, yeah, if you take care of the, yeah, clear look, okay, so these two clearly kind of, yeah, the mirror imaging to each other, non-superimposable, okay. So that's here, this example involves both kind of anti-addition, okay, so anti-addition and also residual selectivity, okay, so goes kind of, yeah, OH goes kind of more substitute carbon. All right. And the synthesis application for the yeah, epoxide, okay, so yeah, that copy it, okay. The synthesis application is kind of, yeah, we can use yeah, this reaction to make the epoxide, okay. All right. So epoxide kind of yeah, remember it's here the yeah, three membrane, okay, with the yeah, oxygen, okay, so inside, okay. All right, and so for this reaction, because naturally you generate some kind of the anti kind of the position of the yeah, OH with Br, okay, so that immediately can yeah, go to kind of yeah, ring closing reactions, okay. So give you one example, okay, so yeah. All right, so we have this alkene, okay, and then we do kind of the yeah, halohydrogen reaction, okay. Yeah, once reaction is done, okay, so yeah. Still draw you guys kind of the yeah. Country, okay. So once reaction is done, okay, so yeah, how kind of the doesn't matter, okay, this time, okay, because the yeah, this kind of symmetrical one, okay, so yeah, doesn't matter, OH goes where it's kind of yeah, Br goes, okay. But yeah, that's still anti-addition, okay. Right, once yeah, this reaction is done, okay, you can find kind of yeah, the yeah, nucleophile, this OH group Br is kind of already anti yeah, positions, okay, so no problem, you can do kind of yeah, the SN2 reactions, okay. We can apply some base, okay, like sodium hydroxide, okay, so close ring like this way, okay. Right, and then you generate kind of epoxide, okay. Yeah. So pretty straightforward, okay. And but yeah, this reaction also need kind of two-step, okay. So you generate kind of the yeah, halohydrogen followed by kind of SN2 reactions, okay. So later this chapter we'll learn another yeah, reaction cases one step, okay. You can convert it alkene into epoxide, okay. Yeah, in addition to kind of yeah, water, okay, so water we generate kind of halohydrogen, okay, so yeah, you can use yeah, the alcohol, okay, as a nucleophile can also do the same reactions, okay, so yeah. Nucleophile, okay. All right, so give you one example, okay, so very similar to kind of yeah, water addition, okay, but this time I use kind of trans alkene, okay, yeah. Cis alkene you generate kind of only one compound, okay, so yeah, no matter how you do it, okay, so eventually you generate kind of yeah, the yeah, kind of yeah, the yeah. Here it's kind of the yeah, we call the yeah, methyl compound, okay, right, and then trans alkene we generate kind of a pair of enantiomers, okay. Right. So actually kind of not water, okay. So here we use kind of alcohol, okay. So maybe highlight, okay. So for the alcohol, okay, so instead of OH, okay, so yeah, you add kind of OR onto kind of CC bond, okay. So after reactions, okay, and then yeah. Yeah, we do this way. Okay, and then yeah, this is the methyl group, okay. Hydrogen, methyl, hydrogen, okay. All right, because yeah, this is kind of the yeah, symmetrical kind of alkene, okay. So yeah, it doesn't matter kind of OR or BR goes, okay. So you can add yeah also OR onto another carbon, okay. So in this case here, the yeah, we can generate kind of it's here the enantiomer, okay. Yeah. So apparel compound, okay. So for the exam quiz, okay. So smart work probably ask you to draw both of this compound, okay. And but for the actual credit homework, okay, or maybe in future if we switch back to kind of the paper-based kind of exam work, okay. So you can just write down kind of one compound and then plus its enantiomer, okay. So just write down plus enantiomer, okay. That should be fine, okay. So all right. So that's here. Keep in mind, okay, alcohol can also do the similar reaction, but instead of here the OH, okay, so OR will add on to kind of as a nucleophile, okay. Right. Okay, so that's here the second reaction, okay. So for the mechanism 2, okay. Now we move to the third one, okay. Yeah, if you guys have any question, type in chat window, okay. So third reaction called kind of here the Oxymorcreation reduction reaction, okay. Yeah, somehow kind of long name, okay. Oxymorcreation reduction, okay. So first kind of Joe, what's the general reaction? Actually, kind of also showed on the slide, okay. So pretty similar reaction. Actually, we already learned before, okay. So convert alkene to kind of alcohol, okay. But this time, okay, so we do two-step reactions, okay. So first step here we use kind of we call kind of mercury acetate, okay. And then it will be the water, okay. So and then second step, okay, so first step actually kind of you also generate kind of this triangle intermediate, okay, so this triangle intermediate called kind of mercurium, okay, mercurium, okay, mercurium, okay, and the similar like brominium kind of triangle, okay, and so second step, okay, so and also followed by kind of ring opening by water, okay, and the second step, okay, just cleave off kind of mercury, okay, give kind of the hydrogen, okay. So the hydrogen, okay, so here, okay, so from kind of the second step, okay. The second step we use kind of sodium borohydride and then sodium hydroxide, okay. These two reagents, okay. So after reactions, okay, so you generate kind of alcohol, okay. Yeah, so that's this reaction, okay. So actually, we can study this reaction together with there's one alcohol formation reaction we learned in the mechanism 1, okay. So acid catalyzed kind of hydration, okay. So remember that reaction, okay. So you have kind of the double bond, okay, and then H plus, okay, with water, okay, and then you can also generate kind of a similar product, okay. So alcohol, okay. Yeah. All right, so that's a kind of question, okay. So why do we still need study for it, okay? So so the reason for that kind of this reaction normally has a much higher kind of yield, okay. So remember for the acid catalyzed kind of hydration reactions, okay. So this kind of reversible reactions, okay. So dehydration, hydration happen at a similar reaction conditions, okay. So that's one give kind of pretty good yield, okay. So this one no problem, okay. So if you follow this reaction condition, pretty high yield for the kind of the alcohol, okay. So irreversible, okay. All right, and the second kind of the advantage related to kind of its mechanism, okay. So for its mechanism, okay, so it's not to follow kind of the carbon we call kind of the carbon cation, okay. So you form kind of this triangle, okay. For this reaction, okay, so mechanism not required, okay. So don't need remember this intermediate, but you keep a little bit idea, okay. So follow kind of the triangle, okay. So in this case, when you open the ring, okay, so won't generate kind of the rearrangement kind of product, okay. No rearrangement, okay. Yeah. All right. And for the regiochemistry, okay, so this one is similar like here the acid catalyzed kind of the hydration reaction, okay. So follow Markov-Nikov rule, okay. So all right, just give you one example, okay. right. So first step, okay, so yeah, from this chapter, okay, the reagent become more and more complicated, okay, so yeah, you have to little bit memorize all the reagent, okay, so the first step kind of mercury with acetate water, okay, second step kind of sodium boron hydrate, okay, sodium boron hydrate NaBH4, okay, NaBH4, okay, and then followed by kind of sodium hydroxide, okay. Right, after reactions, okay, so this one also follow Markov-Nikolov through, okay, so yeah. OH goes to kind of the more substitute carbon, and hydrogen goes here, okay, so maybe show you here. Rich gets richer, okay. Yeah. Right, and so for stereochemistry, okay, so stereochemistry kind of yeah. Although, okay, so this reaction follow Markov two way, generally kind of this yeah, mercury rhenium kind of the intermediate triangle, okay, but the second step, okay, once you cleave off kind of this mercury, okay, mass up in the stereochemistry, okay, so in this case here, some of you maybe already noticed, okay, for this reaction, okay, I also showed kind of the curving bond, okay, so that's been kind of no specific kind of stereoselectivity, okay, so yeah, no anti-addition, no single addition, you can generate kind of all possible product, okay, so yeah. But the advantage for this reaction I already mentioned, okay, so yeah, the high yield, okay, so high yield, okay, and also yeah, no arrangement, okay, no arrangement, okay, so yeah, okay, we'll just see one example, okay. Right. So for this substrate, okay, so yeah, remember, okay, so if we did some kind of acid catalyzed kind of the hydration reactions, okay, and then the real product, okay, something like this. Right. So we have kind of the 1,2 AQ shift, okay. So the methyl group, okay, you just kind of carbon cation here, and then second carbon cation next to kind of quaternary carbon, okay, 1,2 AQ shift, okay, and then you can kind of yeah, eventually OH goes here, okay. But yeah, if you have a same kind of substrate, okay, but yeah, you do kind of oxymorcreation reduction reactions, okay, right? So that's yeah, you get kind of yeah, idea kind of no real product, okay. All right. So for this one, once reaction done, okay. Yeah, that's the product, okay. So yeah, OH goes to kind of the carbon with more AQ group attached, okay, and the hydrogen goes kind of the carbon with more hydrogen attached, okay. So that's the advantage of this reaction, okay. And later, yeah, this chapter we will learn the third reaction, okay. Third reaction, okay, also can convert kind of alkene to alcohol, okay, and give you very special kind of residual chemistry and also stereochemistry, okay. So later, okay. So. All right, okay, so now we move to a little bit harder one, okay, so yeah, that's yeah, we can also do kind of alkyne for the oxymorcreation reduction reactions, okay. So yeah, general reaction shows there, okay, so yeah. Okay, so you have kind of CC3 bond, okay, and then yeah, for the alkyne oxymorcreation reduction, okay, so reaction condition a little bit different from kind of alkene, okay. Alkene we use the here, okay, so yeah, mercury acetate, okay, mercury acetate, okay, for alkyne, okay, so yeah, mercury ion, okay, so actually kind of with some kind of mercury kind of the sulfate, okay, so and then plus some kind of water, okay. And this is just one step reactions, okay. So that's the different from kind of the alkene reactions, okay. So I didn't do this reaction, okay. So my imagination kind of because the mercury sulfate has kind of some kind of certain solubility, okay. So yeah, not so good, okay. So yeah, but can release some kind of the mercury kind of the cation, okay. So yeah, you just kind of add a mercury sulfate, okay. So yeah, probably add some kind of sulfuric acid, okay. So yeah, and then some water, okay. So carry this reaction, okay. Just one step reactions, okay. And then the tricky thing for this reaction, okay, so this reaction is supposed kind of just add water onto kind of CH3 bond, okay, so one carbon pick up hydrogen, another carbon pick up kind of OH group, okay, so yeah, suppose you should get like this, okay. right? But this compound called kind of eno, okay, in stubborn, okay, on alcohol, okay, eno, okay. So this one extremely unstable, okay, extremely unstable, okay. Quickly totemize into something we call the ketone, okay. Right. So you find kind of the hydrogen on the alcohol group, okay, and shift to here, okay, shift to this carbon, okay, and then CT bond become kind of CO bond, okay. So that's a ketone, okay. So this process called kind of keto-eno tautomerization, okay. So just keep in mind, for these two compounds, eno and ketone, okay, node residence and node residence, okay, because they different kind of atom positions, okay. So the resonance, okay, so we only shift the electron, shift the bond, okay, but they'll never move kind of atoms, okay. But here you can see kind of the hydrogen move from oxygen to these carbons, okay. So that's relationship between these two guys we call kind of tautomers, okay. From alcohol. Yes, that's right. Okay. This hydrogen from kind of actually not alcohol from water. Okay, from water. Okay, hydrogen from water, OH also from water. Okay, so you add water on. Okay, all right. And so for eno-keto tautomerization, okay, so mechanism, okay, so you don't need the length, okay, so we'll learn kind of in later later chapters, okay. But you do need to know, okay, so for this reaction, okay, so eventually we generate kind of ketone, okay, not eno, okay, so not eno, okay. So reason for that kind of eno ketone kind of eno not stable, okay, so pretty much okay, quickly kind of become kind of ketone, okay. The hydrogen goes here, okay. So won't stay at kind of eno stage, okay. Eno stage, okay. And for this reaction, okay, so there's no stereochemistry, okay, so because they eventually generate kind of ketones kind of planar structures, okay. But regiochemistry kind of still follow Markov-Nichols, okay, okay. So that's mean kind of when you generate kind of the eno, okay. So the hydrogen goes to carbon with more hydrogen touch, okay, and then OH goes to kind of carbon with the more alkyl group touch, okay. And give you guys kind of one example, okay. All right. So for example, here we have this terminal alkene, okay. Right. And then we apply the Oxymorcreation reduction conditions, okay. Okay, and then so for you guys, okay, beginner, okay, so my suggestion don't need to draw the kind of final ketone in one step, okay, so you can draw the kind of eno first, okay, draw eno first, okay, you know where the oxygen goes, okay, and then the carbon with oxygen touch, okay, become kind of the ketone, okay. Okay, all right. So draw the eno first, okay. So this one, still follow kind of Markov-Nichols, okay, and then hydrogen goes kind of carbon with more hydrogen attached, okay. So the terminal hydrogen, terminal carbon has one hydrogen attached, okay. So after reaction, okay, so the another hydrogen goes here, okay, and then OH goes kind of carbon, just kind of no hydrogen attached, okay, right, okay. So and then once you finish drawing this one, okay, so the whole carbon framework it keeps same, okay, whole carbon framework it keeps same, okay, right, and then only thing you need to change kind of carbon with the OH group attached, okay, so this guy, okay, become kind of single double bond, okay, this guy, okay, single double bond, okay, that's here the how do you draw the ketone, okay, so otherwise yeah, easily get confused, okay, so yeah, all right, so that's here the for the yeah, terminal alkyne, okay. For the internal alkyne, okay, so yeah, that's here the yeah much easier, okay, so right, you guys show just this one, okay, ketone, okay, right. Right, for the internal alkyne, okay, so yeah, we have this as example, okay, yeah. Right, so if we apply similar reaction condition, okay, so yeah, mercury plus 2, okay, and then plus yeah, the mercury, the yeah, sulfonate, okay, and then water, okay. Right, so yeah, this one kind of yeah, pretty symmetrical, okay, so that matter kind of yeah, OH goes kind of whereas kind of yeah, hydrogen goes, okay. So eventually, okay, so if you cannot draw the product in one shot, okay, so yeah, you do it kind of stepwise, okay. All right, one carbon pick up OH, another carbon pick up hydrogen, okay. Right, and then the carbon with the yeah, OH attached becomes kind of ketone, okay. And then the basic carbon framework, you keep everything same. Yeah, that's the ketone, okay. So that's yeah, how do you draw kind of yeah, the product for the yeah, oxymorcreation for the yeah, alkyne, okay. Right. Okay, so that's the mechanism kind of the yeah, 2, okay. So mechanism 2, we learned 3 reactions, okay. First add kind of yeah, the halogenation, okay. So add Br2, okay, 2Br2 or 2Cr onto kind of yeah, the 2Br or 2Cr onto kind of yeah, C double bond. Second kind of yeah, halogen reaction. Third one's kind of yeah, oxymorcreation reactions, okay. All right, and then now we move to kind of mechanism 3, okay. So that's the yeah, another important kind of the yeah, alkene addition, okay. Actually, for the mechanism 3, okay, so yeah, yeah, we only learn one reaction different from kind of mechanism 1 and 2, okay. Mechanism 1, 2, okay, so each mechanism carry a lot of reaction, okay. So for mechanism 3, okay, so the only reaction we learned kind of called the hydroboration oxidation reaction, okay. Yeah. Hydroboration, okay, oxidation reaction, okay. And for this reaction, okay, so yeah, that's here it's acetone. Is this how acetone made? Normally we don't make acetone like this way, okay. So that's yeah, too expensive, okay. So and also yeah, too toxic, okay. So the mercury kind of yeah, the little bit toxic, not good catalyst, okay. And in industrial, that's kind of much cheaper way to make acetone, okay. So yeah, but yeah, in the synthesis, okay, sometimes kind of yeah, if you cannot make acetone by the yeah, easier way, okay, so we do this, okay. Yeah. All right, okay, so yeah, for the hydroboration oxidation reactions, okay, so yeah, that's the third reaction, okay, so yeah, the how do we make alcohol, okay, how do we make alcohol, okay. So the overall reaction kind of yeah, just yeah, show you guys kind of yeah, what's going on, okay. So alkene, okay, again. All right, so this one's also 2-step reaction, okay. The first step, okay, so yeah, we add kind of yeah, boron, okay, BH3, okay. So BH3, okay, sometimes kind of people show that kind of yeah, the BH3, occasionally you can see kind of people show kind of yeah, BH3 and then THF, okay, because the THF also as solvent, okay, so we have to kind of stabilize kind of yeah, BH3, the boron, okay. But sometimes kind of just show kind of yeah, the BH3, okay, so yeah, either way is fine, okay. And then that's yeah, hold kind of yeah, the hydroboration, okay. Second step, okay, so yeah, oxidation, okay, so we use kind of yeah, per hydroxide, okay. That should be kind of yeah, H2O2, okay, H2O2 per hydroxide, okay. Per yeah, hydroxide, okay, hydrogen peroxide, okay, yeah, sorry, hydrogen peroxide, okay, and then with the sodium hydroxide, okay. Hydrogen peroxide with sodium hydroxide, okay, so that's your strong oxidation reagent, okay. after these reactions, okay, so yeah, you generate kind of alcohol, okay. One carbon pick up hydrogen, and then another carbon, okay, pick up OH, okay. So for this reaction, there's kind of very special kind of stereochemistry, okay. So first, okay, if you take a look, you find kind of I draw kind of hydrogen OH on the same side, okay. So that means actually for this reaction, kind of syn addition, okay. And another very special feature of this reaction is kind of this reaction kind of the anti-Markov-Nikov rule, okay. So hydrogen goes kind of the carbon with more alkyl group on, okay, and OH goes kind of carbon with more hydrogen attached, okay. And already 51, okay. So yeah, we stop here the lecture today here, okay. So yeah, next time I'll explain why this one has very special kind of regiochemistry and also the stereochemistry, okay. So yeah. All right. So do you guys have any questions? All right. Should we know epoxide of opening mechanism? Okay, let's see. Epoxide opening, okay, so yeah. Yes, okay, you need to know, okay. So yeah, epoxide mechanism kind of two conditions, okay. One is acid condition, one kind of basic condition. You have to know both, okay. You understand why it's kind of attach kind of attack the last set of carbon or kind of more set of carbon, okay. Yeah. Right. You need to know epoxide opening conditions, okay. All right, so that's all right. So yeah, normally two conditions kind of basic condition, for example, the OH minus, okay. Right, acid condition, for example, kind of H plus, kind of with some kind of nucleophile, for example, kind of just water, okay. So you have to know how do we open the ring, okay. Yeah. Right, it's the actual credit homework. Yeah, actual credit homework due tonight, okay. So yeah, same time as the kind of the exam, okay, time, okay. So yeah. 11:59, okay, 11:59, okay. Yeah, make sure handing time, okay. So if you cannot finish tonight, okay, tomorrow still can handing, okay, but yeah, we will lose the point, okay. So pretty much 1 day 1 point, okay, 1 day 1 point, okay. So yeah, the jobbing box is still open, okay, but yeah, if you handing after the 11:59, okay, so yeah, lose 1 point, okay. Do you have another city root problem we can try, okay. Okay, so in our textbook, there's a lot of CC design questions, okay, pretty good, okay. And so I gave out some kind of the homework, okay, but some I didn't assign, okay, for the actual homework, okay, you also can work on it, okay. So let me see. All right. So for someone want to try the CC design questions, okay, so yeah, you can try the 1090 39, okay, and also let's see. Yeah, 1037, okay, 1037. I assigned some questions, okay, but there are kind of the other question you can work on it, okay. So other question is 1037, okay. And then 1035, okay. So those are pretty good kind of synthesis kind of design questions, okay. So ask kind of how do you finish the reaction? How do you convert kind of mechanism, okay? And how do you kind of convert one compound to another compound, okay? Yeah. So that's since the design the question, okay, so root design question you can work on, okay. All right, so I will stop here the recording of the